Hello, my name is Erfan Khaniki and I'm going to talk about TFNP through the lens of feasible disjunction. This is a joint work with Pavel, Hubáček and Thapen. The complexity class CLS, which stands for continuous local search, was introduced by Daskalakis and Papadimitriou to capture complexity of important TFNP problems solvable by local search over continuous domains. And therefore, the complexity class CLS is contained in the intersection of the TFNP classes PLS and PPAD. And it was plausibly conjectured by Daskalakis and Papadimitriou that actually PLS intersects the PPAD have more problems, like harder problems than CLS. But recently, Fernie et al. Showed that this is not the case and proved that PLS is actually equals to the intersection of PLS and PPAD. So a natural question here is that whether any other intersection collapses among TFNP classes can happen. In this paper, we showed that there is no any other intersection collapses among the classical TFNP classes in the black box setting. So here the following diagram is the diagram of classical TFNP classes. And the green line shows the subset relationship. And we prove that for any non-trivial intersection of any two classes in this diagram, this intersection is not equal to any other classes here. To prove these separations, we connected classes formed as the intersection of existing subclasses of TFNP, which I showed you in the previous slide, with the phenomenon of feasible disjunction in proof complexity. So what is feasible disjunction? So a proof system P has a feasible disjunction property if for any two CNF phi and psi in which phi and psi have disjunct variables, if there is a small p refutation of phi and psi, then either phi has a small p refutation or psi has a small p refutation. So here, phi and psi, there is conjunction, but it's called feasible disjunction. The reason is that if refutation of phi and psi is actually a proof of negation of phi or negation of psi. So if negation of phi or negation of psi has a small proof, then either negation of phi should have a small proof or negation of psi should have a small proof. That's what the feasible disjunction says. And as one of the ingredients to prove the separations between intersection classes, we proved that the proof system Shirali-Adams has a form of feasible disjunction. Also, as an application of the interaction between the relationship between TFNP classes and proof systems, we gave the first examples of proof systems that have feasible interpolation property but do not have the feasible disjunction property, which addresses an issue raised by Pudlak. A proof system P has the feasible interpolation property if for any two CNF phi over variables x and y and psi over variables x and z, where x is the only shared variables and y and z are different, if there is a small pre-refutation of phi and psi, then there is a small circuit C over only the x variables, such that for any assignment to x, C can decide whether phi ay is an unsatisfiable CNF or psi az is an unsatisfiable CNF. And feasible interpolation property and feasible disjunction property are two structural properties of a proof system, and it is natural. It's a natural question to ask whether, like, these structural properties implies each other. Also, before this work, any example of proof system that has a feasible interpolation property also has the feasible disjunction property. And we gave the first examples of two proof systems, RevRes and RevRes-P, in which both of them have feasible interpolation property, but do not have the feasible disjunction property, which is interesting in its own right. And in the last part of this paper, we gave a combinatorial characterization of PPA intersection PPADS. So a measure mu for proof system P is a function that assigns a non-negative real number to any pre-refutation of pre-refutation pi. So like mu can be size, degree, width, etc. And for a CNFF, we define mu of f as the minimum over all mu pi's, where pi is a pre-refutation of f. So which means that size of f is the length of the shortest p-refutation of f. And to give some examples of a proof system, let f be a field and q be a set of polynomials over twin variables with coefficients in f. Then a Nullstellen result over f refutation of q is an identity of 1 is equivalent to sum or over tq times q, where small q is polynomial in the capital Q, and tq's are polynomials over twin variables with f coefficients. And the equivalence here means that the two polynomials are the same modulo the ideal generated by the Boolean axioms and the negation axiom. Another example of a proof system, which we discussed it in next slide, is Charlie Adams. So let Q be a set of real polynomials over twin variables. Then Charlie Adams refutation of Q is an identity which says that -1 is equivalent to V plus, again, the sum TQ times Q. So here TQ, again, is a real polynomial over twin variables, and V is a real polynomial over twin variables too, but with this condition that its coefficients should be positive. As we want to discuss TFNP, we have to define them, and we also need to talk about the relationship to proof complexity. And we separate the intersection classes in the black box setting, which means that we have to define TFNP in the decision model system. So a total search problem is a sequence Rn of relations in which for any Rn, as we can see, is a relationship between strings of length Mn and some solution space. And Mn is a natural number. For any n, the solution space is a finite set. And as we call it total, this means that for any x in 0, 1 to the Mn, there should be some y in the solution space such that x and y are in a relationship with respect to Rn. And a total search problem is in TFNP if, first of all, Mn is quasi-polynomial in n, and second of all, for any solution in the solution space, there should be a decision tree of a polylogarithmic depth such that this decision tree decides whether x and y are in a relationship or not. And as we want to define the class of TFNP problems, we need to define the concept of reductions. Let Rm and Sn be two total search problems. We say that Rm can be reduced in depth B to Sn if there exist two functions f and g, such that, first of all, if you want to compute a solution to Rn for x, we give x to f, and we find the solution to Sn for f of x, which is y, and then we give x and y to g, and that gives us a solution to Rn. And second of all, every bit of fx, and also for each y in the solution space S, the function which maps x to g and y should be computable by depth decision trees. Now, if R and S are two TFNP problems, then R can be reduced to S if Rn can be reduced to Sm, in which M is the quasi-polynomial in N in polylogarithmic depth. Now, to relate proof systems to TFNP classes, we need the following definition. So a narrow family of CNFs is a sequence of Fn in which each Fn is a CNF, such that the following conditions hold. So Fn has quasi-polynomially many variables, quasi-polynomially many clauses, and polylogarithmic many, and its weight is polylogarithmic. And given an unsatisfiable CNFG, there is a natural total search problem, which is called search G, and this total search problem is the following problem. So given a total assignments to variables of G, we have to find a fault clause in G. And as we assume that G is unsatisfiable, this is a total search problem. So if we take a narrow family of unsatisfiable CNFs, it is easy to see that search of f of n is actually a TFNP problem. Now, so from CNFs we get a TFNP problem. Now we want to get some CNFs in a meaningful way from TFNP problems. So let Rn be a TFNP problem, then CNF Rn is the narrow unsatisfiable CNF that says that X is an input with no solution in Rn. And as Rn is a total NP search problem, we get that CNF Rn is actually unsatisfiable. So, and we get that search of CNF of Rn is equivalent to Rn with respect to reduction. Now, to combine all of these concepts, let P be a proof system and mu P be a measure for P. Then we say that a TFNP class A is characterized by P under mu P if for every narrow family Fn of unsatisfiable CNF, search of Fn is in A if Fn has a small refutations in P with respect to mu, and here a small means for logarithms. Here is the characterization of some of the classical TFNP classes in terms of proof systems. So PPA corresponds to Null-Chemsdot over F2, and the measure is degree. PPAD corresponds to unary Null-Chemsdot, and the measure is log size plus degree. PPAD corresponds to unary Shirley-Adams, and the measure is log size plus degree again. PLS corresponds to resolution, and mu is width. CLS corresponds to the proof system rev-res-t, and the measure is log size plus width. As this paper is mainly works about feasible disjunction, we need a formal definition. So let P be a proof system and mu be a measure for P. Then P has mu feasible disjunction if and only if for every CNF F and G in disjunct variables, either mu F could be relatively small with respect to mu F and G, or mu G should be relatively small with respect to mu F and G. Which means again that if F and G has a small refutation with respect to mu, then either F should have a small refutation or G should have a small refutation with respect to mu. As an example, Goose et al. Proved that Null-Chemsdot over F2 has degree feasible disjunction. And this feasible disjunction can be used to prove that PLS intersection PPADS is not a subset of PPA. And this is how it can be proved. Suppose this is not the case, which means that PLS intersection PPADS is actually a subset of PPA. Now take Q as a PLS complete problem and Q prime as a PPADS complete problem. This means that by the characterization between the proof systems and TFNP classes, TNFQ and have a small resolution refutation, and TNFQ prime and have a small unary Shirley Adam refutation. So this means that the conjunction of CNFQN and CNFQ prime N over these two variables have a small resolution refutations and a small unary Shirley Adam refutation simultaneous. Then, as the again correspondence between proof systems and TFNP classes, we get that search of CNFQN and CNFQ prime N is in PLS intersection PPADS. And by the assumption, we get that this TFNP problem is actually in PPA, which means that, again, by the correspondence between PPA and new result over F2, CNFFN, CNFQN, and CNFQ prime N have a small degree new result F2 refutation. And by degree feasible disjunction, we get that either CNFQN have a small degree new result over F2 refutations, or CNFQ prime N have a small degree new result over F2 refutations, which we know this cannot happen by known proof complexity lower bounds. And this completes the proof. To prove the feasible disjunction that I mentioned in the beginning of the talk, we used the well-known concept of pseudo expectation, which is a very standard method to prove lower bounds for sum of squares and Shirley Adams. So we defined a new form of pseudo expectation, which is useful for our application. So for any epsilon bigger than 0, an epsilon pseudo expectation for a set of real polynomials over 20 variables over the degree d is a linear function from monomials of degree at most d with real coefficients to reals, such that it satisfies the four property. And we proved that Shirley Adams has a soundness and completeness theorem with respect to this definition of pseudo expectation. So the soundness theorem says that if we fix the degree d, and if there is an epsilon pseudo expectation for Q, then there is no, like, the specific bound in the statement of theorem bounded refutation of Q in Shirley Adams. And the proof is by just applying the pseudo expectation to the refutation and use its properties to prove the theorem. And for the completeness direction, it says that if there is no R-bounded refutation of Q over degree d, then there is a pseudo expectation for some parameter. And the proof here is by using some convex set based on this assumption and apply the hyperplane separation theorem. As I discussed in the beginning of the talk, we gave two examples of proof systems which have feasible interpolation property but do not have feasible disjunction property. So the proof systems are RevRes and RevRes-T, and both of these proof systems have feasible interpolation property because they are sub-proof systems of resolution. But if we take this psi n and phi n, the conjunction of phi n and psi n over different variables has a small RevRes-T refutations because of the known characterization and relationship between TFNP classes and proof systems. But both of phi n and psi n requires super quasi-polynomial RevRes refutation, which means that both RevRes and RevRes-T do not have the feasible disjunction property. In the last part of the paper, we gave a complete problem for the PPA intersection PPADS. So as I explained before, so we separated all of the intersection classes of the classical TFNP classes, which means that classes such as PPA intersection PPP and PPA intersection PPADS are new entities. So it's natural to investigate their properties. So in this part, we gave a combinatorial complete problem for PPA intersection PPADS. So here is some explanation on how we define this problem, this combinatorial problem. So the leaf problem corresponds to PPA. You are given a undirected graph and then distinguished leaf vertex, which is shown here by the blue color, and you have to find another leaf. In the PPA case, you get a directed graph with a distinguished source, and you have to find another source for a sink. For PPADS, you are again given a directed graph and a distinguished source, and you have to find a sink. And here we define this problem, which we call it leaf or sink. So you are given a directed graph and a distinguished source. Either you have to find the leaf, which means that you forget about the directions, or you have to find the sink with respect to the direction. And we showed that leaf or sink is a complete problem for PPA intersection PPADS. So leaf or sink is in PPA intersection PPADS is easy from these pictures. For the hardness part, let's assume that you have a PPA instance and a PPADS instance, which is a leaf instance and a sink instance. So we get the leaf instance, we put arbitrary directions over its edges, but this new graph is not necessarily a leaf or sink instance. We use the PPADS instance to somehow resolve the problem that might appear here to get a real leaf or sink instance. And here are two open problems. So the first question asks whether PPAD, in particular by PPAD, I mean urinary elution stats with respect to the log size plus degree measure, have the feasible disjunction property. And the second question is that whether there is a natural combinatorial complete problem for PPA intersection PPP. Thank you.